The workshop in Bakersfield, California, existed in the marginal hours. Warren Stockton worked evenings and weekends in a rented industrial space that still carried the faint scent of the machine shop that had occupied it before him. By day, he maintained his position as an aerospace tooling specialist, but the precision skills that earned his paycheck were applied to different problems once the sun went down. On the workbench in front of him sat a component resembling a submachine gun receiver, though the magazine well pointed upward rather than downward. Beside it, a cylindrical prototype magazine lay in pieces, springs, followers, and cartridge guides, all arranged in the methodical sequence of someone who had disassembled and rebuilt the same mechanism dozens of times. It was early 1982, and Stockton had been chasing the same engineering ghost for 3 years. The question wasn't whether high-capacity magazines were possible. They existed, protruding from equipment like awkward appendages that disrupted handling and announced their presence in every tactical context. The real question was whether capacity could coexist with balance. Stockton had studied ammunition geometry with the obsessive focus of someone who believed the answer was hiding in plain sight. 9mm cartridges were roughly 30 millimeters long and 10 millimeters wide. Stack them vertically in a box and the mathematics become punishing. 50 rounds meant a magazine body over half a meter long. But arrange them in a spiral, each cartridge slightly offset from the one behind it, and the same 50 rounds could occupy a cylinder barely 15 centimeters in diameter. The helical concept wasn't entirely new. Historical precedents existed in drum magazines and even some experimental designs from decades earlier, but none had solved the feeding reliability problem that made helical systems notorious for jamming. Stockton's insight was recognizing that the issue wasn't the spiral arrangement itself. It was the transition point where cartridges had to rotate from their storage position into proper feeding alignment. Every helical magazine failed at that critical interface where rotational geometry met linear feeding requirements. So he focused everything on that single moment of transition, designing a track system that used the cartridge's own dimensional tolerances to guide the orientation change. The prototype on the bench represented iteration 17. The magazine body was machined aluminum, chosen for its weight-to-strength ratio and the precision tolerances Stockton could achieve on his milling equipment. Inside, a spiral track wound inward from the magazine's outer wall toward the center, each groove precisely calculated to maintain cartridge spacing while allowing controlled rotation. The spring mechanism was simpler than conventional designs. Instead of a single high-tension spring fighting friction along the magazine's entire length, Stockton used a distributed pressure system that maintained consistent force as the spiral unwound. He picked up a dummy cartridge, dropped it into the magazine's loading gate, and felt it click into the first position of the helix. Testing would come later. For now, the mathematics suggested it should work. The spiral track reduced friction by distributing force across a longer path. The cylindrical housing placed the magazine's center of mass directly above the grip, eliminating the torque moment that made conventional high-capacity magazines so awkward, and the rotational feeding mechanism meant cartridges arrived at the chamber with momentum already established in the correct direction, reducing the spring pressure required for reliable feeding. Stockton set the magazine down and picked up his notebook, adding another entry to the calculation log he'd been maintaining since the project began. The numbers aligned. Tomorrow, he would load live ammunition and discover whether theory survived contact with reality. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Warren Stockton had never intended to become a firearms designer. His career trajectory followed the aerospace industry's expansion through Southern California during the 1970s, specializing in the precision tooling that made high-performance components possible. But aerospace work carried a particular frustration: the gap between engineering elegance and procurement reality. Brilliant solutions often faded in proposal reviews because they challenged established manufacturing relationships or threatened bureaucratic comfort zones. Stockton watched innovations vanish into committee deliberations, while inferior designs move forward on institutional momentum alone. The experience taught him that breakthrough concepts needed demonstrable proof before they entered the negotiation arena. The Helical magazine project began not as commercial ambition, but as intellectual problem-solving. Stockton had grown up around firearms in rural California, learning marksmanship and basic maintenance from his father. When he later encountered submachine gun designs during aerospace contracts involving military tooling specifications, the magazine capacity problem struck him as unnecessarily primitive. Here was an industry that had achieved remarkable sophistication in metallurgy, manufacturing precision, and reliability engineering. Yet it accepted a fundamental design constraint, linear magazine geometry, without apparent question. The assumption seemed so universal that it had become invisible. Initial research confirmed that helical feeding had been attempted before, always with disappointing results. The biartisan helical magazine, developed in Russia during the First World War, demonstrated the concept's potential but suffered significant reliability problems. American attempts in the 1950s and 1960s produced similar outcomes, promising capacity but unacceptable jamming rates. Stockton studied every documented failure he could find, looking for the common thread. The pattern emerged gradually. Every design treated the helical path as a storage solution, but failed to integrate it properly with the feeding mechanism. Cartridges arrived at the chamber exit in random orientations, requiring the bolt to force them into alignment during chambering. No wonder they jammed. His solution inverted the conventional approach. Instead of storing cartridges in a spiral and hoping they would sort themselves out during feeding, Stockton designed the track geometry to actively manage cartridge orientation throughout the entire helical path. Each groove in the spiral included subtle angular guides that rotated cartridges incrementally as they traveled toward the center. By the time a round reached the magazine's exit point, it had completed a precise 90-degree rotation and arrived in perfect feeding alignment. The bolt encountered cartridges that were already properly positioned, eliminating the forcing action that caused binding in earlier helical designs. The engineering required machining tolerances typically reserved for aerospace applications. The spiral track had to maintain consistent dimensions across multiple rotations, with groove depths varying by fractions of a millimeter to accommodate the gradual orientation change. Stockton fabricated the initial prototypes himself, spending hours on the milling machine to achieve the precision his calculations indicated was necessary. Each magazine body required 12 hours of machine time, and he scrapped the first 6 attempts due to dimensional inconsistencies that would affect feeding reliability. The 7th prototype met specifications, and he moved forward to spring system development. By mid-1982, Stockton had assembled a functional system around the helical magazine concept. The receiver was a simplified blowback design, intentionally conventional to isolate variables during testing. If the equipment experienced feeding failures, he wanted to know with certainty they originated from the magazine rather than interactions with an exotic operating system. The receiver accepted the cylindrical magazine from above, with a simple locking mechanism that ensured precise alignment between the magazine's exit port and the chamber. Everything about the design prioritized testing clarity. If the helical concept failed, Stockton wanted unambiguous data explaining why. If it succeeded, he wanted performance metrics that would survive scrutiny from skeptical engineers who had seen helical magazines fail before. The helical magazine's feeding mechanism represented a three-dimensional solution to what most engineers treated as a two-dimensional problem. Conventional magazines stack cartridges vertically, relying on spring pressure to lift each round into position for chambering. This approach works reliably for moderate capacities, but it scales poorly. Adding rounds means adding length, and longer magazines experience increased friction, spring stress, and potential for binding as cartridges stack higher. Stockton recognized that the limitation wasn't spring strength or magazine materials. It was the geometric assumption that cartridges had to travel in a straight line from storage to chamber. The spiral track inside the Calico magazine allowed cartridges to occupy three-dimensional space more efficiently. Picture a parking garage with vehicles arranged on ascending ramps rather than stacked vertically in a tower. Each cartridge in the helical magazine sat in its own defined position along the spiral, separated from its neighbors by the track geometry rather than by compression against adjacent rounds. This distribution eliminated the cumulative friction problem that plagued high-capacity box magazines. In a 50-round stick magazine, the bottom cartridge bears the weight and spring pressure of 49 rounds above it. In Stockton's helical design, each cartridge experienced only the localized forces from its immediate neighbors in the spiral sequence. The feeding process itself relied on rotational dynamics that conventional magazines never access. As the equipment cycled and the bolt moved rearward, it extracted the spent casing while simultaneously allowing the magazine's spring mechanism to rotate the helical track incrementally. This rotation advanced the next cartridge in the sequence toward the exit port. Simultaneously, the track's angular guides, those precisely machined grooves Stockton had spent hours perfecting, rotated the cartridge through its 90-degree orientation change. The entire process happened in the fraction of a second between cycles, with each mechanical element performing a specific geometric transformation. Critical to reliability was the exit port geometry, where cartridges transitioned from the magazine into the chamber. Stockton designed this interface with the same precision philosophy that governed the spiral track itself. The port included a shaped ramp that controlled the cartridge's final orientation adjustment, ensuring it entered the chamber at the correct angle for the bolt to strip it from the magazine and drive it forward. This ramp geometry was the culmination of dozens of prototype iterations, each one slightly different in angle or curve radius. Stockton tested each variation with dummy cartridges, looking for the configuration that provided consistent feeding across different ammunition types and loading conditions. The spring system that powered the helical rotation was Stockton's most elegant departure from convention. Instead of a single coil spring compressed along the magazine's length, he used a constant force spiral spring similar to those found in measuring tapes. This type of spring maintains consistent pressure throughout its travel distance, unlike conventional coil springs that deliver maximum force when fully compressed and weaken as they extend. For a helical magazine, constant force meant consistent feeding reliability, whether the magazine held 50 rounds or 5. The last round fed with the same mechanical advantage as the first, eliminating the weak spring failures that plagued conventional magazines near the end of their capacity. Testing revealed the design's strengths and limitations with equal clarity. The helical magazine fed reliably across different ammunition manufacturers and bullet profiles, confirming that Stockton's track geometry was robust enough to accommodate normal manufacturing variations in cartridge dimensions. Feeding rates were consistent through the magazine's entire capacity, with no decrease in reliability as the spiral unwound. The magazine proved more durable than conventional designs under impact testing. The cylindrical housing distributed forces more evenly than a box magazine, which concentrated stress at the corners of its rectangular body. However, the design was not without compromises. manufacturing complexity remained significantly higher than conventional magazines, requiring precision machining that increased production costs. Loading the magazine was slower than simply dropping cartridges into a box magazine's open top. Each round had to be guided into the spiral track's loading gate and advanced manually until it clicked into position. And while the magazine's capacity was impressive, it wasn't infinite. The helical geometry imposed practical limits based on the cylinder's diameter and the number of spiral rotations that could be machined without making the magazine excessively long. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. Warren Stockton's testing protocol reflected his aerospace background more than conventional development practices. He didn't simply load the magazine, use it until it was empty, and declare success or failure. Instead, he treated each test session as a data collection exercise designed to isolate specific variables and quantify performance across multiple parameters. A notebook system tracked every test: date, ambient temperature, ammunition manufacturer, bullet weight, cycling rate, and any anomalies in feeding or extraction. If the magazine experienced a failure to feed, Stockton wanted enough contextual data to determine whether the problem was systematic or random, temperature sensitive or ammunition specific. Early testing identified several issues that required design revision. The magazine's loading gate, the point where cartridges entered the helical track, initially allowed cartridges to skip past their proper position if loaded too quickly. Stockton redesigned the gate with a spring-loaded detent that physically stopped each cartridge until it seated fully in the track groove. This modification added a tactile feedback mechanism that communicated proper loading to the user. Later testing showed that the detent system reduced loading errors to near zero, even under the rapid manipulation that would characterize field conditions. A more subtle problem emerged during extended use sessions. After approximately 200 cycles through the same magazine, feeding reliability began to degrade slightly. Stockton initially suspected spring fatigue, but disassembly revealed that the issue was lubricant migration. The constant rotational motion of the helical track gradually displaced grease away from high-friction contact points, concentrating it in low-stress areas where it served no function. The solution required reformulating the lubricant specification to favor higher viscosity compounds that resisted migration under centrifugal forces. Stockton consulted with aerospace lubrication specialists who dealt with similar problems in rotating mechanical assemblies, eventually settling on a synthetic grease originally developed for high-speed bearing applications. Temperature testing revealed the design's environmental robustness. Stockton conducted trials in a rented cold storage facility, testing the magazine's functionality at temperatures down to -20 degrees Celsius. The helical system showed no degradation in feeding reliability, primarily because its distributed spring design avoided the cold-related stiffening that affected conventional box magazine springs. High-temperature testing, conducted in the summer heat of Bakersfield's industrial district, similarly confirmed that the magazine maintained functionality up to 50 degrees Celsius without experiencing pressure-related feeding failures. Durability testing followed rigorous impact protocols, subjecting loaded magazines to falls from various heights and orientations. The cylindrical housing proved remarkably resistant to deformation, with the curved geometry distributing impact forces more effectively than the flat panels of conventional box magazines. Even after impacts that would dent a steel box magazine severely enough to compromise feeding, the Calico magazine typically showed only cosmetic damage to its exterior finish while maintaining full functionality. This resilience wasn't accidental. Stockton had intentionally chosen the cylinder geometry, partly because aerospace experience had taught him that curved structures handle impact loading better than planar surfaces. By late 1982, Stockton had accumulated sufficient test data to confirm the helical magazine concept's viability. Feeding reliability exceeded 98% across multiple ammunition types and environmental conditions. The magazine's weight-to-capacity ratio was significantly better than conventional designs. A 50-round Calico magazine weighed less than a 50-round drum magazine, while occupying considerably less space. And the positioning of the magazine above the receiver produced handling characteristics that multiple test users described as superior to conventional layouts, particularly for sustained use where the centralized weight distribution reduced fatigue. The data supported proceeding with formal development, but Stockton faced the practical challenge of transitioning from prototype to production. His workshop methods, individual machining of each magazine body, hand-fitting of components, and iterative adjustment couldn't scale to commercial manufacturing volumes. The helical magazine required production techniques and quality control processes that would maintain the tight tolerances his prototypes demonstrated were necessary for reliable function. Stockton began documenting manufacturing specifications with the same precision he'd applied to the design itself, creating technical drawings that communicated not just dimensions, but the critical nature of specific tolerances that affected feeding geometry. The final curiosity that defined the Calico M960's legacy wasn't revealed during its development. It emerged years later when other designers attempted to apply the helical magazine concept to different calibers and systems. Each attempt encountered the same fundamental constraint: the helical feeding geometry that worked so elegantly for 9mm cartridges became progressively more problematic as cartridge dimensions changed. Larger calibers required proportionally larger spiral tracks, increasing magazine diameter until the handling advantages disappeared. Smaller calibers reduced the dimensional tolerances to levels where manufacturing consistency became prohibitively expensive to maintain. Stockton himself discovered this limitation when exploring variants of his original design. A prototype chambered in .45 caliber required a magazine cylinder nearly 8 inches in diameter to maintain the same capacity as the 9mm version. At that size, the magazine's bulk negated the handling improvements, transforming it from a balanced system into an unwieldy one whose weight distribution felt awkward to experienced users. Conversely, attempts to adapt the helical concept to .22 caliber cartridges revealed that the smaller dimensions made the spiral track's orientation guide so minute that they were vulnerable to debris contamination and manufacturing variations. The 9mm cartridge occupied a dimensional sweet spot where helical feeding geometry could express its advantages without encountering crippling limitations. The cartridge was large enough that the spiral track's features could be machined with tolerances achievable in production manufacturing, yet small enough that 50-round capacity didn't require an excessively large magazine cylinder. This specificity explained why the Calico remained primarily a 9mm system despite attempts to expand the concept to other calibers. The engineering wasn't universally scalable. It was optimized for a particular set of dimensional relationships. Stockton's recognition of this constraint influenced how he approached the commercial development. Rather than marketing the Calico as a revolutionary platform that would dominate multiple market segments, he positioned it as a specialized solution for applications where 9mm capacity and handling characteristics were paramount. This included law enforcement entries for specialized rescue operations, personal protection scenarios requiring sustained capability in confined spaces, and security applications where magazine changes created tactical vulnerabilities. The system found its niche not by being all things to all users, but by excelling at specific tasks where its unique characteristics provided genuine advantages. The helical magazine's legacy extended beyond the Calico system itself. Stockton's engineering approach, treating magazine geometry as a three-dimensional optimization problem rather than a fixed constraint, influenced subsequent developments in ammunition storage systems. While few designers attempted direct helical implementations, the underlying principle of distributing cartridges across multiple spatial dimensions rather than stacking them linearly appeared in various forms. Casket magazines that staggered cartridges in overlapping columns, quad-stack designs that arranged rounds in complex geometric patterns, and even modern polymer magazine designs that used internal geometry to reduce friction, all reflected variations on the spatial optimization principle Stockton had demonstrated. What made the Calico's final curiosity particularly illuminating was its demonstration that engineering excellence doesn't guarantee universal applicability. The helical magazine worked brilliantly within its optimal parameter range and struggled outside it. This wasn't a design flaw. It was a fundamental characteristic of specialized engineering solutions. The same geometric principles that made 50-round capacity practical in a compact package also imposed boundaries beyond which the concept lost its advantages. Stockton's achievement wasn't creating a universally superior magazine system. It was recognizing a specific problem space where helical geometry provided elegant solutions to constraints that defeated conventional approaches. By the mid-1980s, the Calico M960 had established itself in specialized market segments, earning a reputation for reliability and handling characteristics that defied expectations for high-capacity systems. Stockton's original engineering vision, demonstrating that magazine capacity didn't have to compromise balance, had been validated by years of field use across various applications. The system never achieved mass-market success or large-scale adoption, but it accomplished something potentially more significant. It proved that fundamental design assumptions in mature industries remain negotiable if someone is willing to question them rigorously enough and pursue alternative approaches with sufficient engineering discipline. The Calico M960's legacy exists less in production numbers than in conceptual territory. It occupies the space where established engineering assumptions encounter rigorous questioning. Warren Stockton's helical magazine didn't replace conventional designs because it wasn't meant to. Instead, it demonstrated that capacity limitations everyone accepted as inherent to the feeding problem were actually consequences of geometric choices that could be altered if someone understood the underlying physics clearly enough and possessed the machining skills to implement alternative approaches. This distinction matters because technical development, like most mature engineering disciplines, operates within paradigms that become self-reinforcing. Conventional solutions persist not because they're optimal, but because they're established. Manufacturers know how to produce them efficiently, users understand how to operate them, and regulatory frameworks accommodate them without requiring new evaluations. Innovations that challenge these established patterns face resistance that has nothing to do with technical merit. The Calico encountered this resistance throughout its commercial development, confronting skepticism from users who had seen helical magazines fail before, and manufacturers who questioned whether the design's advantages justified the retooling investments production would require. What separates the Calico from earlier helical magazine attempts is the engineering rigor Stockton applied to the feeding geometry problem. Previous designers had treated helical storage as the innovation and hoped the feeding process would sort itself out. Stockton inverted this priority, recognizing that storage efficiency was meaningless if cartridges didn't arrive at the chamber in proper feeding orientation. His spiral track system, with its precisely calculated angular guides that rotated cartridges throughout their travel path, solved the reliability problem that had defeated earlier helical designs. This wasn't incremental improvement. It was identifying the specific mechanical failure mode that made helical feeding unreliable and engineering a geometric solution that eliminated that failure at its source. The Calico's influence appears in unexpected places throughout subsequent development. Designers working on conventional magazine systems began paying more attention to internal geometry and friction reduction, recognizing that Stockton's success with helical feeding reflected deeper principles about how cartridge storage and feeding mechanics could be optimized. Polymer magazine designs that emerged in the 1990s incorporated internal ribbing and surface treatments that reduced friction, direct descendants of the distributed friction reduction approach Stockton had pioneered. Even the aesthetic language of design was influenced. The Calico's distinctive silhouette, with its cylindrical magazine mounted above the receiver, challenged conventional assumptions about how such a system should look and encouraged experimentation with alternative form factors. Educational impact extended beyond professional designers. Engineering students studying the Calico encountered a case study in constraint questioning and geometric optimization. The system became a reference example for demonstrating how mature technologies contain hidden optimization opportunities if designers are willing to examine fundamental assumptions rather than accepting inherited wisdom. Stockton's work illustrated that breakthrough innovations don't always require revolutionary new materials or exotic manufacturing processes. Sometimes they emerge from asking why existing approaches accept specific limitations and whether those limitations are truly inevitable. The Calico M960 remains in limited production decades after its initial development, serving specialized markets where its unique characteristics provide genuine advantages. The system never achieved the commercial success that would make it ubiquitous, but ubiquity was never the measure of its importance. What matters is that Warren Stockton, working in a rented workshop in Bakersfield during the early 1980s, demonstrated that a problem everyone considered solved, how to feed cartridges from a magazine into a chamber, still contained unexplored solution spaces if someone approached it with fresh geometric thinking and sufficient engineering discipline to implement unconventional concepts reliably. The final lesson the Calico offers is about the relationship between specialization and innovation. The helical magazine worked brilliantly for 9mm cartridges and struggled with other calibers precisely because it was optimized for specific dimensional relationships rather than attempting universal applicability. This specialization, often perceived as a limitation, was actually the source of the design's excellence within its optimal parameter range. Engineering progress doesn't always mean finding solutions that work everywhere. Sometimes it means understanding a particular problem space so thoroughly that you can achieve performance levels impossible with more generalized approaches. The Calico M960 embodies this philosophy, standing as evidence that questioning established constraints with rigorous engineering discipline can yield innovations that reshape how an entire industry thinks about supposedly settled problems. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.